Hello and welcome to another lecture session of Introduction to Astrophysical Fluids. In this lecture, we will discuss a very interesting topic, that is the turbulence in MHD fluids. Okay, so MHD or magnetohydrodynamics is the monofluid model of a plasma. So it is true that in astrophysical or space physical fluids, we always see clear signature of turbulent motion. Now, how to categorize this, or how to classify this, or actually how to perform a quantitative study of this type of turbulence is a great question. Okay, and this question is not easy to answer. So, depending on our interests in different frameworks, we use different type of models. Sometimes we are happy with the hydrodynamic turbulence model. Sometimes we have to take the plasma property into account. Sometimes, and just the monofluid model MHD is sufficient for that. Sometimes we have to go beyond. Okay, then some sophisticated sophisticated fluid, plasma fluid models. So MHD is the simplest plasma fluid model. As you know, that the plasma fluids can be also described in the framework of multi-fluids. Okay, and so that this type of turbulence can also be very much interesting, but of course given our interest. Okay, so and if certain questions are still not answered, then we have to go beyond even, so we have to take the kinetic effects into account. But here, just for this course, or just for just to initiate you to the turbulence in plasma, we will simply give you a very introductory overview of MHD turbulence. Okay, also very qualitatively, I will just enter into some mathematical details whenever it is necessary. But once again, the mathematical rigor is not really followed over here. So just as I said, that I mean, uh, similar to ordinary hydrodynamic fluids, turbulence is also found in MHD fluids, and actually, to be very honest, in plasmas. And one of the easiest way to model this plasma turbulence is through the turbulence in MHD fluids, because we know the MHD equations. Okay, so to understand how what are the features of an MHD turbulence, we have to start from the basic equations of MHD. Okay, and again, like as we did in the case of hydrodynamic fluid, we will just consider an incompressible fluid, because incompressible fluid turbulence is much more easy to handle and much more easy to see what is happening. The phenomenology is much more easy, or how to say, much more concrete to discuss. Okay, so in this framework, we will only be constraining ourselves into the discussion of incompressible hydrodynamic and MHD fluids. Okay, although for your information, that in many cases in astrophysics, okay, we have to consider compressible MHD turbulence, okay, or compressible hydrodynamic turbulence. Now, just to start with the incompressible MHD equations, this is divergence of V and divergence of B both vanish, and then the momentum evolution equation becomes del V del T plus V dot nabla V is equal to minus gradient of P by rho plus curl of small b cross small b plus nu times Laplacian V. And if you remember, small b is nothing but the magnetic field normalized to a velocity when this is given by b, the magnetic field divided by root over mu 0 rho. rho is the constant density of the incompressible fluid. Okay, so then the induction equation can be written as del V del T is equal to curl of V cross B plus the magnetic diffusion term, that is eta times nabla square B. Okay, as you know that for ideal MHD, of course, we just need this, but here we are talking about turbulence in MHD fluid, so we don't need an ideal MHD equation, but this is the normal resistive MHD equation. Whenever we have this term, we say the corresponding MHD to be the resistive MHD. So these are the equations of resistive MHD. Okay. Now, if you remember the normal hydrodynamic Navier-Stokes equation, then the nonlinear term which was present was this one, and the viscous term was this one. Okay. Now in this case we have a lot of terms, and certain terms are actually subject to give the nonlinearity. So here the nonlinearity can be of various types. So in the force equation or the momentum evolution equation, you have the nonlinear terms like V dot nabla V, and from here, if you remember that there will be a term of magnetic tension which should look like B dot nabla B, and this is also nonlinear. So this one is nonlinear in V, this one is nonlinear in B. Then becomes the induction equation. So induction equation in true sense, it is linear in B only when V has no feedback on B. But for magnetohydrodynamic turbulence, okay, for an MHD plasma, B and V, they affect each other. So we cannot say that this is simply a linear equation in B. Okay, so actually V dot nabla B and B dot nabla V both are non-linear equation in that sense, because in V you have B and in B you have V. Okay. So we have now all this type of non-linear terms, and we know that in order to ascertain turbulent flow regime in case of an MHD fluid, of course, both the force and the induction equation must be dominated by the non-linearity, and that is the normal necessity. Okay, that every equation should be dominated by the non-linearity. Now, for force equation, such a regime is achieved by having the Reynolds number with a very large value. So Reynolds number is the ratio of the nonlinear term, kinetic nonlinear term, to the kinetic dissipation term. Okay, and there is another term which is the magnetic tension term by the kinetic dissipation term, and that also should be large, but this term is not in general very much discussed, only because that if we say that the fluid is very fastly moving, okay, then already this term is having a large Reynolds number, and this basically makes the whole momentum evolution equation dominated by the nonlinearity. So we really don't need to have a large value for this. However, if your velocity is not very large, then you can have to have a look on this. But then the problem is that if your velocity is not large but your magnetic field is large enough, then so the problem is that velocity is in the denominator. So when it is small and magnetic field is, let's say, large, then there will be a non-trivial competition to look at, and in certain cases that can be also interesting. But here for our current case, we will simply be talking about the large value of Reynolds number to be the necessary condition for the nonlinearity domination, the dominance of nonlinearity in the force equation. For induction equation, we have two type of nonlinear terms as we have discussed, b dot nabla v and v dot nabla b, and the ratio of these two things to the corresponding magnetic diffusion or magnetic viscosity term. I mean, magnetic viscosity is a very unusual term, but magnetic diffusion term, okay, or the resistive term, gives us another quantity. So both of them actually, okay, can lead us to some quantity which should look like this one, VL by eta. So the numerator will exactly be the common Reynolds number, but the dissipation term, okay, the dissipation or the viscosity coefficient will now be replaced by the magnetic diffusivity, and this is known as magnetic Reynolds number. And for the induction equation to be dominated by the nonlinear effects, the value of this magnetic Reynolds number should also be very, very greater than 1. That means it should have a very large value. Okay. Now at this point, I have to make one point, that it is true that this Reynolds number and magnetic Reynolds number, they are introduced in our course as I introduced. They are, they should look like just the parameters for deciding whether a fluid flow is turbulent or not. But in general, Reynolds number or even magnetic Reynolds number, if you remember, okay, if you understand correctly the association, you will see that these two things are actually very important to represent, or to, how to say, to manifest another property of fluid flow, which is the similarity property. That means that if, let's say, if your now just take the case of the normal Reynolds number, okay, its expression is simply VL by eta. Now if your the geometry of the of the flow field is same, but the length scale is now twice, and the velocity is also changed, okay, accordingly, and eta is also changed accordingly, so that finally this ratio is simply having the same value as that of the previous value. Then one can simply say that there's two systems, two flows are actually similar in nature. So in some sense, you can smartly, just by smartly choosing the velocity and the coefficient of viscosity, you can actually change the large scale dimension of the flow field, okay, and then the basic properties of the flow field will not be different. For example, the transition from laminar to turbulent flow. So if, let's say, at some Reynolds number nearly 10 to the 3, or let's say 5000, the flow of certain flow gets converted, or gets how to say that, has a transition from laminar to turbulent flow, then when the flow field is basically 10 times larger, just by choosing the corresponding velocity and the coefficient of viscosity, you can simulate, or just by doing the inverse thing, that means you can choose the length scale to be 10 times smaller, but again by smart choice of velocity and the coefficient of viscosity, you can again simulate the fluid flow with the same type of property. That means again you will see that when the Reynolds is of the order of 5000, then in that system you can produce turbulence, or directly from laminar flow. Okay, so the message is that, just the Reynolds number, the use of Reynolds number is, that's why very much useful, that you can actually simulate a very big large astrophysical system or a galactic system, just by smartly choosing or keeping the Reynolds number value intact. Okay. Okay, so now coming to our main point, that for an MHD flow to be turbulent, its necessary condition is that both the Reynolds number and the magnetic Reynolds number should be very greater than 1. Okay. Now, just like normal hydrodynamic fluid, energy cascade is also a universal property in MHD turbulence. Okay, that's something which is already been studied in several research and also been founded in, also is found in several observation or in experiments. Okay, now it is true that for hydrodynamic turbulence, we had the phenomenology of Kolmogorov. So Iroshnikov and Krishnan, they said, well, not really, but they are now thinking in a different way, which we will discuss here. So to understand Iroshnikov-Krishnan phenomenology or IK phenomenology, let us recall the incompressible MHD equations in terms of Elsasser variables. Just remember, when I talked or discussed Elsasser variables, I said that this variables, this writing, the expressing the incompressible MHD equations in terms of Elsasser variables, they actually useful when we will study turbulence in MHD fluids, and that's exactly the case which we are now discussing. So del Z plus minus del T is equal to minus Z minus plus dot nabla Z plus minus nabla PT, that is the total pressure, plus D plus minus Laplacian Z plus D minus plus Laplacian Z minus. So these two terms are the dissipative terms. So for instance, we are not really interested in those dissipative terms because in turbulence we are mostly interested in the nonlinear terms which are actually dominating these dissipating terms. Okay. So here you again see, if you, in case you have forgotten, that the nonlinear terms are of the type of Z minus dot nabla Z plus or Z plus dot nabla Z minus. There are no such like Z minus dot nabla Z minus or Z plus dot nabla Z plus. So they have a cross type of nonlinear terms. So it simply says that Z plus is advected by Z minus and vice versa, right? Now we know that any small perturbation, when we talked about the wave modes in MHD, so we said that in incompressible MHD, any perturbation actually propagates in any weak perturbations, first order perturbation propagates with a speed which is equal to the Alfvén speed, and Alfvén speed is corresponding the is corresponding to the phase speed of the Alfvén mode, okay, which is the only incompressible mode of an MHD fluid. So in normal hydrodynamic fluid, we do not have any wave mode for incompressible fluid, but for MHD, incompressible MHD, we have one mode which is called the Alfvén mode. Now we in this case we have to actually consider, in order to proceed, the presence of a considerable mean magnetic field small b0. So here actually this simply says that capital B0, but when I am saying small b0, that is the capital B0 normalized by root over mu0 rho. Okay, that's the same thing. And then the total magnetic field can be written as the mean magnetic field or the background magnetic field plus the fluctuation with a tilde sign. And also we consider for velocity, this background velocity is 0 and all the velocity field is nothing but the fluctuation. That we can always do just by sitting to a reference frame which is moving with the mean velocity of the system, and that is possible because the fluid equations are Galilean invariant. Okay. Now if you just decompose every magnetic field as B0 plus B0 B tilde, then actually you will be obtaining an equation which should look like this. Okay, and you will see that um, just a minute, minus plus, it should be minus plus. Okay, yeah. So you will see that del z tilde plus minus del t minus plus b0 dot nabla z tilde plus minus plus z minus plus dot nabla z plus minus, and then you have this gradient of pressure term plus the dissipative term. Now there are two things. One thing is that what is the meaning of this term? This term simply says that both the z plus and z minus, they are advected with a speed which is equal to the Alfvén speed but in the opposite direction. So z plus is advected in the negative direction. Okay, so it actually moves with a minus b0 velocity. So b0 is the equivalent mean velocity, a mean magnetic field normalized to a velocity, but this is also here in this case is equal to the Alfvén speed. Okay, so b0 so z plus propagates, z plus tilde basically propagates with velocity minus b0 and z minus propagates with a velocity plus b0. Okay, and then this one simply says that then, so this is not a non-linear thing because b0 is uniform background magnetic field, and this one gives us an account of the non-linear interaction of the perturbations. So the perturbation in z plus is advected non-linearly by perturbation of z minus and vice versa. So this non-linear interaction between z plus and z minus is basically the reason for energy cascade in incompressible MHD turbulence, and that is the essence of Iroshnikov-Krishnan phenomenology, which simply says that, let's say you have two wave packets, this one is z tilde minus, okay, so it will move to the positive direction with some velocity va which is equivalent to our b0. Okay, so I took this picture from my thesis where I used the Alfvén velocity to be equal to VA. Okay, and Z tilde plus would move with a velocity minus VA. Then just after interaction, this perturbation has now deformed to Z plus tilde plus delta Z plus tilde, and the same thing will be for Z minus. And now this one is still moving with a velocity minus VA and this one is still moving with a velocity plus VA, or maybe a slight change in velocity. But at least they are deformed. And this is exactly equivalent to the fragmentation of eddies from one size to the other, because after deformation this has a different size. Okay, and as people have seen that the energy cascades both in incompressible MHD and incompressible HD in 3D, energy cascades from larger scales to smaller scales, then we can say that after deformation both of them get shorter. Okay, so according to Iroshnikov-Krishnan phenomenology, energy is cascaded from larger to smaller length scales due to the nonlinear interaction and subsequent deformation between two counter-propagating Alfvén wave packets. Okay, so this type of, this Z tilde plus minus, we just call them Alfvénic wave packets because they are small perturbations moving with Alfvén speed. Okay. Now, Iroshnikov and Krishnan, they considered a specific case of isotropic MHD turbulence with a considerable B0 to obtain some spectral prediction like Kolmogorov's minus 5/3 prediction for MHD turbulence. So they said that, okay, our system has a considerable mean magnetic field, but the turbulence is isotropic. Okay, which is not really practical, as you know that a strong mean magnetic field always makes the system axisymmetric. That means the system's property along the mean magnetic field and in the plane perpendicular to the mean magnetic field are quite different in general. And they also considered, for simplicity, no, not okay. They also considered that for an adequate deformation of Z plus minus, a large number of collisions are required. So this is the fundamental difference between the hydrodynamic turbulence and MHD turbulence. In hydrodynamic turbulence, one AD, so the AD got fragmented into two, as I said. So the AD gets elongated in one side and then gets in order to keep the incompressibility, it gets compressed in the perpendicular direction, and then at one point it gets fragmented. But the fragmentation process is just once, so this is a one shot process. On the other hand, here they considered that one collision between Z tilde plus and Z tilde minus is not sufficient for the energy cascade. For the sufficient, for example, for let's say for becoming from a length scale L to L by 2, for example. And for that, they assumed that actually a large number of collision is necessary. And then what happened, after some very heuristic arguments, one can show that the characteristic time for the nonlinear transfer is neither L by Z tilde type, okay, which is the case for normal hydrodynamic case, that L by V. So here it should be L by Z plus minus whatever, but and nor L by B0, because B0 is another characteristic velocity in this system. So but if you call this tau L and you call this as tau AL, then the resultant transfer time from one scale to the other, okay, is actually tau L square by tau AL. So this square by this, okay, and this simply leads to another spectral prediction, which is for isotropic MHD turbulence, which is not minus 5/3 but E of k should then scale as k to the minus 3 by 2. Okay. However, IK phenomenology does not quite represent the reality, as I just said, as all the incompressible MHD flows become anisotropic or rather axisymmetric in the presence of a considerable B0 or mean magnetic field. And in fact, one can argue that in the presence of B0, MHD turbulence follows Kolmogorov phenomenology in the plane perpendicular to the B0. So in the plane perpendicular to the B0, one actually can expect a minus 5/3 spectrum rather than a minus 3 by 2 spectrum. Now in solar wind, a minus 5/3 spectrum is often found for magnetic energy power spectra. That is just for your information. Okay. And a minus 3 by 2 spectrum is observed for velocity power spectrum. But that can actually look like, yeah, the velocity power spectra follows maybe the IK phenomenology. Well, nothing to do with that. They have some plausible explanation, but it is true that this minus 3 by 2 spectrum has nothing to do with IK phenomenology. Okay. Now, finally, what I am trying to emphasize that whatever your minus 5/3 or minus 3 by 2, in practice, when you do some simulation or some observation and analysis, most of the cases your spectral indices are in such a range that whether this is minus 5/3 or this is minus 3 by 2 is not really easy to understand. Okay, and actually there are several variations. Most of the cases you can see that it can be minus 1.55, sometimes it can be minus 1.6, and then the whole range of variation can lie within the range of errors. And finally, for the other scales which are, lower or smaller than the normal MHD scales, okay, people actually use much more sophisticated plasma fluid models or even kinetic models, okay, to describe or to explain the corresponding spectral slopes. And finally, last but not the least, in case of describing various type of spectra, power spectra, energy power spectra, or magnetic, kinetic energy power spectra, or magnetic energy power spectra, or the total energy power spectra, actually in the case of astrophysics, okay, and even for the solar wind, it is seen that sometimes the consideration of the compressibility, that is the fluctuation of density, is of prior importance as well. Okay, I personally am interested in studying the compressible effects in space and astrophysical plasma turbulence. Okay, so this was somehow a very brief overview of turbulence in normal fluids and plasmas. And just to tell you once again that turbulence is something which is of potential importance in finding in explaining several phenomena starting from the star formation. I have not really attacked that point because the role of turbulence in star formation, okay, how it regulates the star formation, is totally possible if we try to if we introduce the compressible turbulence. But in this framework of non incompressible turbulence, what I was just to try to convey that starting from solar wind plasma, there are magnetospheric plasmas, okay, all these plasmas give a clear signature of turbulence. And according to our interest and the length scale, concerned length scale, we try to study using different type of uh, turbulence, different type of turbulent models, fluid models, okay. And when we are interested once again in the length scales which are much larger than the ion inertial length scale, then we try to fit this in the framework of MHD turbulence. Okay, thank you very much.